Hello and welcome to another Smart Grid Systems class. Today's class, we would continue demand side management. Particularly, we're going to speak about demand side response. And from next week, we're going to start with renewable energy. And then after that, we will continue with microgrids. I would make an announcement for your second exam, which is gonna be this last week of April. And I'll post another set of homeworks. And also, I would post an announcement about your final project as well, uh, because it would take a few weeks, at least 3-4 weeks to start that. So this weekend, I will start with the final, and I would post an announcement for the final project as well. So for the demand side response, we already spoke about time-based rate programs, or what we called usually when time-based programs comes in mind, we usually mean TOU, which is time of use pricing, but we have other methods as well, other methods of tariffs for pricing the time of use as well. So the first one that we already spoke about a little bit is the time of use, or TOU pricing. We also have real-time pricing, or RTP, and the inclining block rate as well. So time of use, I already mentioned the dot curve. So the time of use actually is opposite of that. And usually during the off-peak hours, um, these are, by the way, off-peak hours, so this is in reverse. Um, you're gonna have a lower price for off-peak hours, and then we have mid-peak and peak hours, which is gonna be the price is gonna increase. These peak hours usually are in early afternoon and night and early mornings, and the off peaks are usually at the middle of the day, at noon. And by the way, this is different in different parts and of the country. So if, for example, you live in California, Texas, um, compared to someone that lives in New York or Canada, it's going to be a different scenario. So based on where you live, you're going to have a different pricing and different time of use pricing tariff. And then we have the hour of the day pricing as well. That fluctuates more than the time of use. So if, for example, there is, um, let's say, during lunch hour, which is a rush to go everyone to the restaurants, and this is a downtown area, you're going to have a little bit higher price at that time. It's going to dip after lunch, for example, and so on. So depending on the hour of the day, this has more flexibility than the time of the use. And then we have the inclining block rate. Mostly this is used by the kilowatt hour that people consume. So if someone is consuming less than 20 kilowatt hour, it's going to be in a lower category. And if someone consumes more, it's going to be in a higher bracket. And the prices fluctuate depending on how much you use on the time of the day as well. So if you lose less, you're going to be charged, for example, 7 cents per kilowatt hour. If you use more than 20 kilowatt hours, you have a bigger restaurant, so you're going to be charged more. This is to encourage people to use less power. And we also have the critical peak pricing, or what we call a CPP. In this case, customers respond for a short time period. The CPP tariff plan has higher rates for critical periods designated by the utility. The CPP is similar to TOU tariff structure, except that the time and the price are not fixed. One example for this: imagine there is like an event or a Super Bowl, for example. That's a good example, and everyone is watching TV. They're at their homes. So this during that event, the power companies could cost more because there's going to be a much higher demand during that. And you can see here that the blue line is the fixed price, but the dotted line is the variable price, and it could move both ways in vertical and horizontal, meaning the price could change, go up and down, and also the time of the use, the time of the day usage could change as well. This is a table that we already shared in the previous class on the customer enrollment and retail time-based rate programs by regions. And I already mentioned that sometimes people prefer comfort over having a lower price. So you may charge them higher during peak hours, but some people prefer to turn on their washer dryer during the peak than to wait during off-peak hours because they have to go to work or something. So it's not that it will always have a positive effect. Sometimes, again, as mentioned, people would pay a higher price but prefer to do their chores at the times that they want to do, like their laundry or so on. Or they would prefer to have a more comfortable temperature, but they are willing to pay higher prices. That's when we have the direct load control, or what we call a DLC. The utility has direct control over consumers' loads. We have flexible consumers, which favor incentives than comfort. We have the flexible loads, which are deferrable, interruptible appliances, like as mentioned in the previous class, the refrigerators, AC units. And those are not on a regular daily basis. And consumers usually lose the control over their appliances occasionally when upstream control signals are received. One example is the PG&E Smart AC program, which is in California. PG&E is a Pacific Gas and Electric company. It's an investor-owned utility with publicly traded stocks. It provides natural gas and electricity to most of the northern 2/3 of California, and its headquarters is in San Francisco, California. The PG&E has a smart AC program, and it's usually between May 1st and October 31st during the hot season. And in case of an energy shortage, in that period, May 1st to October 31st, the PG&E will send a signal to your smart AC device directing your AC to run at a lower capacity, therefore lower the demand. It usually increases the thermostat and defers the time of the day use of the AC, and it will turn it off at certain times. The motivation is that on hot summer days, energy demand may increase substantially because thousands of customers are using their air conditioning units. This leads to a high price and affects the grid reliability. The actions that the PG&E may take is they may remotely activate the smart AC device on those days in order to help maintain adequate power supplies and avoid power interruptions. The duration of the smart AC events, the days can be as short as an hour or two and no more than 6 hours in a day. The incentives that the PG&E provides is to install a free smart AC device. It's usually a smart thermostat on your air conditioner AC and give you a $50 for participation. And the qualification for this is for the participants must have standard central AC conditioner and or heat pumps. The air conditioner doesn't require to be a new high-tech smart one. Usually what they do is they would provide a free smart thermostat or a thermostat with discounts, such as an Ecobee or a Nest or a smart thermostat. Um, just most recently, CenturyPoint Energy and APNG uh, in Houston have started the program as well. They provide like that free smart thermostat, Honeywell or Ecobee or Nest, or they give it with big discounts, it's from $200 to $60, $70, and you would install them. And if you give them access to your smart thermostat, they will give you incentives and discounts on your rates as well. So they've just started that in Texas as well. Um, so the operations with demand response, the direct remote control, uh, the benefits of including the DR in power systems operations. The DR adds great flexibility to system operations. The DR can reduce system control costs. Um, the demand response control can relieve network uh, congestion under both normal situations and emergency situations. Then we have the corrective demand response, or what we call the CDR. And the CDR, or corrective demand response, we have two type of controls in the system. We have preventive control and we have corrective control. So the preventive control, all the actions are taken before a disturbance occurs. Usually, it's connected to the forecast. So if there is a heat wave or there's a storm coming or there's a freeze storm, um, the system will reduce the demand or even increase the response time and the generation to prevent any shortages and blackouts. So the system would pre-position the system to withstand an event without any adjustment in the post contingency situation. Again, these actions are done before. Nowadays, they're using a lot of AI and machine learning algorithms to be able. One example, if there's, as mentioned, it's a Super Bowl game, um, and a lot of people are going to watch them and be indoor. So what they would do, they would reduce demand in an industrial setting, for example, or AC, and then navigate the demand to the consumers. And then we have the corrective control. This actions are taken after a disturbance occurs. Usually these actions, the disturbance are not predictable. Um, the preventive ones, usually you can predict them by the time of the day or the day of the year, or if there's, as mentioned, a weather event. But the corrective control, it's just a sudden disturbance in the system. This withstand an event with adjustment in the post-contingency situation. Some actions may still need to take before a disturbance occurs. They are implemented shortly after a contingency, for example, 10 minutes after that. And the example would be using a demand response service as a corrective control action in the post-contingency situation. And this is a graph that shows the OPF SCUC with corrective demand response, or CDR. And you can see that usually there is a delta T, 10 minutes, which is the outage response time. Uh, and this will be implemented. This will implement CDR if there are contingency induced system congestions. This shows the graph, the flow chart for this SCUC with the CDR. You can see that this is the SCUC and this is the response time here. We have the base case constraints, which are the generator's output limits, the reserve requirements, the power flow constraints, the nodal power balance, the hourly ramp rate constraints, the startup constraints, the minimum up, minimum down constraints, which gives us the base case constraints and the post contingency constraints. And therefore, we would have the post contingency modeling for line contingency. We would have the post contingency modeling for generation contingency, and we would have post contingency nodal power balance with CDR. And this table shows us um, the test system for IEEE 24 bus system. This is both the generator contingency and transmission contingency modeled. And we can see without the CDR and with the CDR. And with the CDR, the cost is about $15,000 less. And you can see the CDR due to line outages, it's non-applicable here, but here it's going to be 25.46. And you can see the time is much less as well. This SCUC CDR model benefits by significantly faster solve time. The CDR action required for only few critical bottleneck line outages at various time periods, and the CDR actions were required for only a few large generator outages to maintain system reliability. And as you can see, the overall cost saving is allowing $15,000 or 14, to be exact, 14,996 for the system with the CDR. And this is another graph which shows the SCUC with CDR. This is the total system cost and cumulative the DR shifted for different scenarios. And we have 5 scenarios here. We have 80 to 90%, and then 90 to 100, 100 to 110, and 110 to 120 and above that. So we have 2 low load scenarios, 80, 90, and we have a base load scenario, which is 100%, so 80, 90, 100, 110, and 2 high load scenarios, which is 110 and 120. The CDRs are not implemented for 80% load since the base case network and the post contingency network are not congested. So we have pretty low, and we don't need to be implemented when the load is below 80%. Above 80, 120% load, the SCUC and the SCUC CDR are infeasible because the system is overloaded. Nothing can compensate that. But for the CDR actions are absorbed when we have a 90 to 110% along with the economic benefits. In this graph, the green is the total CDR for generator contingency. The yellow shows the total CDR for line contingency, and you can see that here for line contingency goes up. For the generator contingency, it comes down. And the blue line is the total cost for a SCUC CDR, and the dot line is the total cost for SCUC alone. And you can see the difference that we had around $15,000 here, 685,000, and this is 670,000, around a 50,000 with and without CDR. At a 90% load, only consists of the CDR action due to the line outages. At 100 to 110%, CDR actions are from both line and generator outages. And at high load scenarios, 110%, the SCUC is infeasible whereas SCUC CDR provides a feasible solution for utilizing the flexibility associated with CDR. So above a certain point, we can only use the SCUC with the CDR. And this gives us another table for the generator commitment solution with and without the CDR. And you can see this is with the CDR and without the CDR. And this shows when the system is always on, always off, marginal units, and so on. And we can see that there's a less number of committed generators over 24 hours. And you can see it obviously here as well. When we have a CDR, you have less generator commitment and compared to the line contingency. So consideration of flexibility through CDR favors long-term reliability of generators through infrequent generator startups. Now, we learned that the CDR gives us significant advantages. So demand response, again, some advantages is that it eliminates the need to have an idle generator, so spending a lot of extra money on transmission and reserve power generation by simply controlling the demand. But it comes with some cons as well, some problems. One problem is the cybersecurity response. So just to summarize the benefits and what is a demand response. Demand response is a program that encourages flexible customers to modify their consumption level and pattern, such as temporarily reduce their electricity consumption. DR needs pre-signed contracts between utilities and customers. Thus, customers would get compensation and financial incentives by participating in the demand response programs. The advantages of demand response are, in addition to the traditional generation side management, demand response provides system operators an alternative option to manage the grid. The DR helps defer the need for new sources of power and network upgrades. As mentioned, we don't need to have idle generators, extra capacity of generations, and it's going to reduce the investment, the CapEx and OpEx significantly. But there is a problem. One disadvantage of DR is potential cyber attacks and cyber vulnerabilities. The DR signals that is supposed to be sent to the customers may be hacked and not actually delivered to the customers. There won't be any changes in the electric demand, but the attacker can change the associated measurements to make the operators believe their signals have been followed by customers. Based on such false information, system operators may take improper actions and negative physical consequences, such as outages, may occur. False demand response signal and load measurement injection cyber attacks methods and models would be studied, which again, these would send erroneous DR signals while hacking measurements to make the attack undetectable. This is the illustration of power grid real-time operations. On the left, we see the system in normal operation, and on the right, there's a system under the FSMI attack. And we can see here, there's no cyber attack. The cyber attacks are shown with red arrows. We have the SCADA, same thing that we had before. Bad data detection and state estimation. We would have the RTCA, SCED. We would have optimal dispatch on generators and controllable loads. Then we will control the physical systems and change the measurements and so on. goes back to the loop. But when we have the system under cyber attack, we would have the FSMI cyber attack, which would attack the DR and system measurement. The previous cyber attack we saw was on the generators and on the relays and transformers and the measurements. Here, the attack would be on the loads, measurements of the loads. And I'll explain in the next slides how it's done. So for example, it would send a false measurement, and the operator will think that on the load side, it has turned off the AC unit while the AC unit is still running. So you would have higher load than the operator would see. So this is a DR under cyber attack. This is incorporated DR and SCD OPF. Total demand, you would see a high demand system. You would have an orange, a medium demand system in gray, and a low demand system in green. This is a test system for IEEE 24 bus system. There is cost for utilizing DR and SCD. And here you can see the line loading level on targeted line 23 under FSMI attack for various scenarios. We have a high demand. We have a pre-attack system and post-attack, medium demand and low demand. And the demand, you can see that it changes the loading rate. And when changing the loading rate, the system thinks it has a high load, it's going to decrease it, but in reality, it won't decrease. And it's going to have, we're going to have outage and problems and overload in the system. The total system cost and cumulative DR shifts for different scenarios are shown here as well. It has minimal effect on low demand, some effect on medium effect, but it has a high effect on higher demand systems. So again, this time it manipulates the demand side instead of the generation side, and it causes problems and outages, and it may damage the transmission lines and the transformers and so on. That's it for today's class. If you have any questions, just please email me. Again, I will post an announcement about your upcoming exam at the last week of April, and also we're gonna have I will send an announcement about your final project as well. I've already posted the quiz, the podcast, and the notes for today's class. And if you have any questions, just please let me know. And have a great weekend. Thank you.